So today we're going to be talking about section 2.5 from the textbook, which covers the properties of the derivative. And this basically, we could rename this so you can see, I think below the screen here, at the bottom of the screen here, there's 2.5 properties of the derivative, and in parentheses it says chain rule. Basically, you could rename this chapter to just the chain rule, because that's kind of the big property that we're taking away from this is going to be the chain rule, and that's the one we really are going to spend a lot of time focusing on. But we are going to start with a few other properties here in just a second. Basically, when we start dealing with multivariable functions, we have a notion of partial derivatives, but we also have this thing called the total derivative, which is the matrix of total derivatives, or matrix of partial derivatives. The total derivative is the matrix of partial derivatives. And we reviewed a little bit of that yesterday at the end of lecture, but also you've hopefully been looking at the 2.3 homework assignment and seeing kind of computing some of them. It's basically just you put all possible partial derivatives into one matrix. And so these properties of the derivative are going to be properties specifically of that matrix of partial derivatives. So let's take a look at the basic rules here. We're going to focus on these a little less in the homework, so I'm just going to go through these so you have them in your notes, basically. But basically, these just say that the matrix behaves the way you expect it to behave. So you have this function f of x. So I guess one thing I should say here is f is a function which goes from r n to r m. Okay. So then we can multiply that function by a scalar, and the effect it has on the matrix of partial derivatives is that it's just the scalar times the matrix of partial derivatives. So the matrix of partial derivatives of the scalar multiple of f is just the scalar multiple of the matrix of partial derivatives of f. Okay. Basically, this says we can move scalars outside of this D operator. And you might be thinking like, okay, well, this is like a big matrix thing. Why do I care? But if you look at what this says about individual partial derivatives, it says that individual partial derivatives also behave this way. Individual partial derivatives, you can pull out scalar multiples. That's what this is saying in terms of the individual partial derivatives. And that's what all of these properties are saying. So the other thing you get here is with addition. So if you take the derivative, the total derivative, or the matrix of partial derivatives of the sum of two functions. So I guess I should also throw in here g is also from Rn to Rm. They have the same. So you can add them together. And this is just the sum of the matrices of partial derivatives. Okay. And then you might be thinking, okay, how do I add matrices together? But all that means is that you add each of the components. So if you have, you have two matrices of the same size, you first row, first column, add those together. Second row, first column, add those together, and so on and so forth. And you just add all of the things together, and you get this new matrix of the same size. Okay. 3 and 4 here are a little more interesting. So here we in particular let m equal 1. And that's going to give us that's going to allow us to take the product of two functions, because if m equals 1, right, then that means these are just scalar valued. So I'm just multiplying numbers here, right, because the outputs are just numbers, they're not vectors. And so the matrix here, right, so far this has been like, the rule about scalar multiples, constant scalar multiples. Here we have the rule of sums, right, a sum rule. So this here is going to be like a product rule. And we know from single variable calculus that when we start getting into products and then quotients, the rules tend to look a little bit different, right? And so this is definitely no exception, right? So the derivative of this is going to be, or the total derivative of this is going to follow the product rule. It's going to look very similar to the product rule we already know, right? So it's going to be g of x times df plus f of x times dg, right? Which is exactly what you'd expect from a product rule like this, right? So it's, if you memorize your product rule, it's like, it's it's f of x times g prime plus, or f prime times g plus f times g prime, except that the primes become these matrices of total derivatives here. And this is now a scalar multiple of a matrix here. And so that's so the notation is a little different because what's actually happening is a little different, right? These are matrices now. And so you have something slightly different happening, okay? So as you can imagine, there's going to be something similar for the quotient rule. Okay. So for the quotient rule, we're going to have g of x df plus or minus f of x dg, all of this divided by g squared. Right? Again, totally what you'd expect from the quotient rule, right? Very similar to the quotient rule from single variable calculus. So basically what all this is telling us is that the matrix of partial derivatives behaves very similarly to the way we would have talked about just a regular old derivative in calculus, right? In single variable calculus. Okay, cool. Cool. Okay. So these are our basic rules. Okay. And on the next slide, we're going to talk about the chain rule. So let's move on to that. Again, if you didn't get a chance to write all of this down, I know it's a lot here. So the notes do get posted, so you can take a look at them later if you need to. So let's look at the chain rule, which is we're going to spend most of our time today. Okay, so the chain rule here. So now I want to point out a couple of things. So we have F and G, but I want to notice something that in the last slide, F and G had the same domain and range, right? They would both started in Rn and ended up in Rm. Now, F is starting in Rn and ending in Rm, but G is starting in Rp and ending in Rn. Okay, so we're allowed to compose these, right? So here we take the composition of functions. Remember that. Maybe I'll make a little note here. Okay, so the composition here only makes sense if the range of G is in the domain of F. So for the sake of this class, often what that means is just they should have, so the number of outputs of G should equal the number of inputs. There's a little bit more to it than that. For example, like if sometimes there's certain inputs that cause F to like divide by 0, then you should make sure that that's not an output of G or something like that. And so you should be careful with some of those subtleties too. But mostly what we're looking for is that the number of outputs of G matches the number of inputs of F. And that's the when we compose this way. If we compose the other way, so G of F, then we'd want the opposite. We'd want the outputs of F to match the inputs of G. Okay. So there's some questions asking like this stuff about this on on WebAssign. So they're like multiple choice questions. So you should this should be kind of a note to help you out in that. So again, this is just, how we talk about compositions of functions. In single variable land, oftentimes we can kind of just compose either way, and it doesn't really matter because it's just every function has one input and one output, so you can always just compose. Now, you could, I picture them like Legos or like cables that you're plugging into each other, and if the two ends don't match, then you can't really plug them into each other. And so you can, there's only or maybe there's only one way they plug into each other. For example, and we'll see some examples, more concrete examples of this. If M and P are different numbers, then you can compose this way, but you can't compose the other way. F of G makes sense, but G of F doesn't make sense. Okay, cool. I hope I've driven that point home. Okay, so the real, what we're trying to get at here is the actual, the calculus here, which is to say that, okay, so we talked about compositions and like when are we and aren't we allowed to compose functions, which is, maybe like a concept on its own, but we're saying, okay, so let's imagine we can compose these two functions like we have here, like we have the n and the n match, so we can compose those. What happens when we take the derivative of that composition, the total derivative of that composition? So you might remember the basic product rule, the single variable product rule. And this is going to be analogous to that, but I think it takes a minute to figure out how this is analogous to that. And since the derivatives of these functions are matrices, right? If you remember your formula for the chain rule of single variable calculus, some people like to say that it turns that composition into a multiplication. But that's a multiplication of numbers. Here, it's going to turn it into a multiplication of matrices. And so let's see exactly what I mean by that. So this is going to be df with g plugged in times dg. Dg. Okay. So just like remember in the single variable case, in the single variable case, you had like h prime would be f prime of g times g prime, right? You take the derivative of the outside with the inside stuff plugged in times the derivative of the inside, except now that those derivatives are matrices, and so that multiplication at times is going to be matrix multiplication. Okay. Cool. I think the best way to see this is we can go through some examples here. Okay, so let's take a look at this example here. So we have this function f of xy. So it's a function in two variables, has three outputs. So there's two inputs, three outputs. And then g of t, so there's one input and g has two outputs. And so this is going to make sense. And one of these compositions is going to make sense. In this case, it's f of g makes sense, right? Because I have two outputs of g. I could plug those into the two inputs of f. So then I can make sense of f of g. The other direction wouldn't make sense. If I tried to plug g of f, right? There's three outputs here, but there's only one input in g. There's no way to plug these three into g in a way that makes sense. I mean, I can try to plug like maybe I add them all together and then plug in there, but that doesn't. It's not going to be the same for every problem, right? And so there's only one way to compose these in a way that makes sense, right? So take the outputs of this guy, plug them into the inputs of this guy. So the way we're going to do this is by computing the matrix of partials for each of these separately and then multiplying those matrices together. So with that's what the chain rule tells us we're allowed to do. So let's compute df. So this is going to be, remember, the matrix of partials. You take d of you go through the coordinates. So each row is, I like to think each row is the gradient of one of these coordinates. So this first row, you just focus on the first coordinate and you take all possible partial derivatives. So the derivative of this with respect to x is 2x. The derivative of this with respect to y is 0, right? Because there are no y's. So as y changes, this doesn't change. Okay. So that's the first row. The second row, you focus on the second coordinate here and you take the derivative with respect to each variable. So here, the derivative with respect to x is just 1, and the derivative with respect to y is also 1. Okay. And now what about here, x times y? So x times y, the derivative of that with respect to x is y, and the derivative of that with respect to y is x. So we end up with this matrix of partial derivatives. Okay. Okay. Now, what if I take dg? This matrix is going to be a 2x1 column matrix, right? Because there are 2 coordinates. So you remember each row focuses on just one of the coordinates. And then there's only one variable. Each column focuses on one variable. And so there's only one column and 2 rows. So we take the derivative of cosine of t with respect to t. So we get negative sine of t. And then we take the derivative of sine of t with respect to t, which is cosine of t. Okay. And we can multiply these as we see them. But the thing I'm going to do first is I'm going to say, hey, look, this still has x's and y's, but ultimately f of g is just a function in one variable. So this should only be one variable in my final answer. And what that is if you remember in the formula here, we're supposed to take df and plug in g. So if you remember right here, you got to plug in g into the derivative, the matrix of derivatives for f. So here what that means is that x is going to equal the x coordinate of g and y is going to equal the y coordinate of g. So if we plug in, we're going to plug in g of t and we get 2 cosine of t, 0, 1, 1, and then sine of t, cosine of t. Okay. Okay. So by the chain rule here, d f of g is going to be the product of these two matrices. So it's going to be 2 cosine of t times 0, 1, 1, sine of t, cosine of t, times negative sine of t, cosine of t. Okay. Gonna give myself some room here. Okay. So this is equal to, I'm going to do this matrix multiplication. There's going to be 3 rows in the final answer and 1 column in the final answer. Again, I have a 3x2 matrix times a 2x1 matrix. So I should end up with a 3x1 matrix, right? So again, brushing up on our matrix multiplication. A little bit of that comes up in the worksheet today in case you need the practice. So again, doing the matrix multiplication here, I'm going to end up with a 3x1 matrix. Give myself some space here. So I'm going to get negative 2 sine t cosine t right? So that's this times this plus 0 times cosine of t. So the 0 times cosine of t just disappears. And then now over here, I get negative sine of t. The second row, I'm going to get negative sine of t plus cosine of t, right? Again, I get, remember, I'm taking this row and I'm taking the dot product with this column, right? That's how we multiply these matrices. So 1, 1 dot product with negative sine t cosine of t. So that gives me negative sine of t plus cosine of t. Now, lastly, we end up with the dot product of sine t cosine t with negative sine t cosine t. So that gives me negative sine squared t plus cosine squared t, which is almost a Pythagorean identity, but not quite, so it doesn't simplify. And we're done. That's the whole thing there. Okay. Can you explain the matrix multiplication again? Yeah. So let's see. Again, I have a 3x2 matrix, right? So there's 3 rows and 2 columns. So 3x2 times a 2x1. So that should give me a 3x1. That's just mean, that's like a sanity check thing you should always be doing, right? Like, okay, if I'm multiplying matrices, especially if you've been practicing on WebAssign, a lot of time in WebAssign, that gives you like the matrix, like the entry, like you have to type in your answer, but it gives you like all of the entries already. It tells you like exactly the size of the final matrix. And so if you're doing it by hand, you're going to want to like double check that you know how big it's supposed to be. Okay, so for the first row here, remember there's only one column, so just the first row here is going to be the dot product of this first row with this column here. Now, something that might be confusing you, hopefully I made it clear. I should be using parentheses here to make it more clear that's a t and not a plus sign, okay? So basically, I multiplied this 2 cosine of t by this negative sine of t, and then 0 by cosine of t, and added those together. Again, 0 by cosine of t, that's going to be 0. So I just end up with this negative 2 sine t cosine t. That's what this first row is, okay? The second row here is going to be the dot product of 1, 1 and negative sine t cosine t, right? So people pointed out when we were learning matrix multiplication that matrix multiplication is just doing a bunch of dot products, right? And so for this this first column, second row, which again is just the only column, second row, it's going to be the second row of the first matrix dot product with the only column of the second matrix. And so I do this and this dot product, and I get negative sine t plus cosine of t. And then lastly, I do this bottom row with this only column, and I get sine of t times negative sine of t, which is negative sine squared of t, and then cosine of t times cosine of t, which is cosine squared of t. Okay. Does that help? Make sense? Make a little more sense? Yeah. Yeah. Yeah, so for these, if the composition only works in one direction, like it does here, like you can only compose f of g, you can't compose g of f, like we were talking about, then the matrix multiplication will only work one way. So if you try to multiply the other way, you're going to get weirdness happening. Okay. Cool. Any other questions? So there's like layers of stuff going on. This starts to combine a lot of what we've been talking about so far, right? We have to do a bunch of different partial derivatives. We have to multiply matrices. Those are kind of those are like two of the big things we've been doing in this class computationally. And so this might seem kind of like, I don't know, like why do we have to multiply matrices if we're just trying to take a derivative? But in a lot of cases, the matrix multiplication is going to be easier than actually computing the derivative by hand. Because what I mean by that is, right, f of g, we can just take this, plug into here, and then just compute the matrix of total derivatives, right? plug in cosine of t for x and sine of t for y in here, and just compute the total derivative. But this here is, in some sense, going to actually make it a little more straightforward. The derivatives that we have to end up doing are going to be easier in this case because they're less complex. Okay, and a lot of times what you're going to end up seeing is you're going to have to do a bunch of chain rules when you're taking the partial derivatives anyway, but they're going to be smaller, like single variable chain rules instead. Okay, so sometimes this is just a little more, it's just taking care of everything at once, taking care of all of the partials at once. Okay, I think I have another example for us here, or I might have two examples of the next topic or the next sort of case. We'll see. Okay. If you have questions, feel free to slow me down. But I'm going to move on to the next slide, which I think is another example, but we'll see. Yes, it's another example. Yes. So here we have a function, the square root, 1 over the square root of x squared plus y squared. Now we could compute the gradient of this function just like by, compute the derivative with respect to x and then compute the derivative with respect to y, which is a totally fine way to approach this problem, but we're going to have to do chain rules in each of those. So what we want to do is we want to break this down as, so f is a function, right? F goes from R2 to R, right? Because it has 2 inputs and 1 output. And so what I'm going to do here is I'm going to break this up in 2 ways. So I'm going to say that this f, I'm going to let h of xy equal x squared plus y squared, and then g of t equals 1 over the square root of t. Okay. So then f is equal to g of h here, right? Because f is just the composition of taking this and plugging it into this. Okay. So what this is going to let us do is remember the gradient is secretly just a special case of the matrix of total derivatives, of partial derivatives, right? The matrix of partial derivatives is just all possible partial derivatives. But if you have a scalar valued function, that's exactly what the gradient is, right? The gradient is just take the partial with respect to x and take the partial with respect to y. And so then by my chain rule here, this is going to be dg with h plugged in times dh. Okay. So let's go ahead and compute this. So dg, well, this is going to be kind of silly because this is a single variable function with scalar value. So it's one input, one output. So the size of this matrix is going to be kind of funny. It's going to be a 1-by-1 matrix. So it's one entry at total, right? So 1 row, 1 column. And in total, this is going to, so we take the derivative, right? G prime of t is going to be negative 1/2. So yeah, so this is t to the negative 1/2. So bring down the negative 1/2 and then 1 over t to the 3/2, right? So it's t to the negative 1/2. So bring down the negative 1/2 and then subtract 1. So it's t to the negative 3 over 2. So we get this here. So that's what we get here. But remember, we have to plug in h. So I'm actually giving myself a little more room. So we have negative 1/2 times 1 over t to the, or I just made a mistake. So x squared plus y squared to the 3/2, right? Cool. So this is our dg with h plugged in. Okay. It's just the derivative of this guy with this plugged in. Times, now this here is actually going to be a matrix because there's 2 inputs and 1 output. So 2 inputs means we'll have 2 rows and 1 output means we'll have 1 column. Is that right? Nope, scratch that, reverse it. It's going to have 1 row and 2 columns, right? one row, two columns. I still get mixed up about which one is which, but right. So the number of rows is the number of outputs you have, and the number of columns is the number of inputs you have. So that's why we're going to have one row and two columns. So we take the derivative of this with respect to x. That's going to be 2x. And the derivative with respect to y is 2y. Okay. And now I take the matrix product of these, which seems weird because this is a 1-by-1 matrix, but I have a 1-by-1 matrix and a 1-by-2 matrix. So these should multiply together just fine and give me another 1-by-2 matrix. And so when I do that here, the first row here by the first column here is going to give me -1/2 times 2x over x squared plus y squared to the 3/2. And then over here I have -1/2 2y over x squared plus y squared to the 3/2 here. And then just if I want to, kind of a couple of things I'm noticing is, first of all, this 2's cancel on both of these. And second of all, because I'm talking about the gradient, I should probably write this row matrix as a vector instead of as a matrix, because it's asking. Usually when they write this notation, so maybe I can annotate this here as, so here when they write this notation, they usually want a vector. And when they write this notation, they usually want a matrix. So I went into matrix world to do all my work, but then at the end, I'm going to convert back to a vector, which is not really a conversion because you just write the same stuff with different notation. Throw a comma in between. Okay. Cool. So this one, right? So chain rule is going to kind of a hard one to get. Like for the sake of this section, for practicing the chain rule, you're going to use the chain rule every time. If you see a problem like this, you're gonna break it down like this. But then, like, when you think of it as a tool that you're learning moving forward, you might think like, okay, when do I know if I need to use the chain rule? And for that, it's like you see a composition here. It might be worth doing the chain rule. It might make your life easier. But in this case, it might have actually been quicker to just compute the partials of this guy, right? Like maybe we could have done just the partial of this with respect to x and gotten like here, and then the partial of this with respect to y and just gotten straight here. But sometimes it's going to be harder to see exactly how to do that, or it's just going to be more complicated because maybe there's like other x's and y's and stuff. And so it's going to be a little more complicated in different situations. And so it's going to be kind of hard to see like, okay, should I use the chain rule here or should I not? Now, if it's like a written problem and you need to show work and it says use the chain rule, then you use the chain rule, right? Because that means that we're testing whether or not you actually know how to use it. But in general, it's going to be kind of hard. It's one of these that it takes time to kind of figure out like, okay, would this have been easier using the chain rule, or would this have been easier if I just hadn't used the chain rule? It's going to be it's going to take time. Depends on how much you practice the chain rule too. Cool. Topics. The next topic is what is basically a special case of the chain rule. And it's called, in the textbook, it's called the first special case, because in the textbook, there are these two different special cases. The second special case we won't really talk about because it's not as important. This first special case I think is more interesting, and so and if you look at the homework, doesn't really talk about the second special case. So I wanted to focus on this first special case here. And basically what we're noticing is that what I've done is I've said, okay, oops, these are kind of reversed here. So F goes from N to R. So I should say Rn to R, and then G goes the other way. It goes from R to Rn. So you can think that this is like a scalar valued function in multiple variables. F is, and G is just like some path in Rn. Right? If we now have the vocabulary to say things that way, right? But in general, you have these two functions. And the point is that I guess you can see here, there's a hint as to what's happening. This here is just a, I use the regular D and not the curly D, right? Normally we've been talking, when we do the partial derivatives, we talk about curly D or something about like the matrix of total derivatives. And this is just the old fashioned D. That's because f of G, if we do the composition here, f of G, right? So f of G, the confusing part is the way it's written is like, it looks like, oh, f and then G, but no, f of G, because you work from the inside out, you start with G. So G takes something from, starts in R, then G puts it in Rn, and then F puts it back in R. And so this is going to go to R. So now this is just a single variable scalar valued function, which is exactly the types of functions we dealt with in single variable calculus. So the derivative of this guy is exactly just the regular old derivative that we had in single variable calculus. And so you can say, okay, what's that derivative? But what ends up happening is that this is basically a, you can think of this as a 1-by-1 matrix. And so you can compute this using using the chain rule df with G plugged in times dg. Okay. But then something even more interesting happens. You can think of this instead of as matrix multiplication. You can say, hey, well, f is a scalar valued function with multiple variables. So df is actually just the gradient of f, still with G plugged in. And G is a path, right? So you have a path. Anytime you have something with one variable, this vector we get as output, in the last section, we were calling G prime, right? Remember, we usually call them C, so C prime, but here we called it G, that's fine. And so what we actually have is a dot product of these two vectors. This is now a vector and this is a vector. And so we can just take a dot product of these two vectors. Okay. And so instead of thinking of it as matrix multiplication, right, you'd end up with a, oh gosh, I'm gonna mess this up. You'd end up with a row matrix here and a column matrix here. Yeah. So this is a row matrix and this is a column matrix. And so when you multiply a row matrix by a column matrix, so I'm going to do a hand gesture that may or may not be helpful. If I have a row matrix times a column matrix, then there's only one row and one column. So I just multiply those together as if it was a dot product, right? That's kind of how I picture it happening in my head, but maybe it's not super helpful for you. But that's kind of what's happening. So basically you're just instead of treating this as a row matrix and this is a column matrix, just treat them both as vectors and take their dot product. Okay. And so that's kind of what's happening. That's what we're doing here. Okay. So in this special case, in other words, where one of your functions is scalar valued and the other one is a path, and you're allowed to, compose them. So in a way that their composition is just single variable, scalar valued. Then the derivative of that is just the dot product of these two derivatives here, or these two vectors here. Okay. So let's see some examples of this. Let's see this in action. Okay. So we have f of xy is equal to x times y, and g of t is equal to e to the 2t cosine of t. So notice this has two inputs and one output. So this is f goes from R2 to R, and g has one input and two outputs. So g goes from R to R2. This is saying compute the derivative of the composition, because if we compose these, if we took this and plugged in here, okay, we just get a one variable input and one thing output. Okay, and so this is just a regular old derivative. We can do it by actually plugging in, but what we want to do is use the formula from the last one. So d f of g dt is going to be the gradient of f with g plugged in times g prime of t. Okay, and then this times here is the actual dot product, because these are vectors. So as a vector, the gradient is going to be, so the derivative of this with respect to x. So we have y, and then the derivative of this with respect to y, so that's x. But we need to plug in g. So this isn't quite done yet. And G prime of T, right, as a vector. Again, we can do it as a matrix, but you end up with this column matrix. Yeah. And so you want to, you can just think of it as a vector. So this is 2e to the 2t, right? That's the derivative of this with respect to t. And then the derivative of this with respect to t, which is negative sine of t. Okay. And then here we need to plug in g. So for y, we plug in cosine of t, and for x, we plug in e to the 2t. So that should be a comma there. So this is cosine of t, e to the 2t, dot product with 2e to the 2t, negative sine of t. Okay. So now let's go ahead and take this dot product, and we get 2e to the 2t cosine of t plus, or I should say minus, because this negative sign, minus comes from this negative sign, minus e to the 2t sine of t. And that there is our derivative. Okay. Cool. Any questions about that? Again, we use the chain rule to turn this into just a dot product of these two matrices here. Okay. So now if we would have plugged this in, so for the results, there is a minus sign, or is that a dot sign? Yeah, this is a minus sign. Yeah, I'm subtracting these. Again, the minus is coming from the sign here. Negative sine of t. So like, alternatively, without using the chain rule here, without using the first special case of the chain rule, you can say that f of g of t is just equal to e to the 2t cosine of t, right? Because it's just f of xy is just x times y. And if you plug in g of t into that, you get this times this. So you just what you get. And so if you go to compute df of g dt, you use a product rule and you end up getting exactly the same thing. Okay, product rule. Okay. And so then like, this is kind of saying like, okay, we have this product rule, and when we plug in, it's a product rule, but if we don't plug in, we can just do it, think of it as a dot product here. And again, the reason we do this is because the derivatives that we actually end up doing are much easier, right? So here we took the derivative of xy with respect to x and with respect to y. That's not too bad. Then here we just take the derivative of these parts of these things separately, and then it kind of works out. Okay. Cool. Any questions on this? Any other questions? Okay, I have one last example, and I think we're going to move on to the next section. We have time to move on to the next section, just for a couple of slides from the next section. Oops, didn't work. There we go. So here's one last type of problem that we might see. So this one, it just throws a lot of information at us, which can be overwhelming. But it turns out that usually when you see a problem with like a lot of information in it, usually maybe it's hard to figure out what it's actually asking. and how to do it. But once you figure it out, you realize that, oh, they've given you a bunch of information. There's actually not a lot of computation. And so in this case, we have these two functions, which they never give you a formula for. So that's why at first this seems harder, because everything we've done so far, we've had nice formulas that we can compute derivatives of. But for this one, we're never given the formula. We're just told, F has 3 inputs, 1 output, C has 1 input, 3 outputs. So we know we're going to be allowed to plug them in. And in fact, F of C is just going to be a function from R to R. So it's going to be single variable, scalar valued. Okay, which means that the derivative is just the old-fashioned derivative, and we want to solve it at t equals 3. Okay, well, according to the chain rule, right? Or I should say the special case of the chain rule, df of c dt at t equals 3 is going to equal the gradient of f at c of 3 dot product with c prime at 3, right? This is just me using the chain rule here, or the special case of the chain rule, dot product of the gradient with g prime. And we just plug in 3 into the innermost function here, okay? But if we look up here, this becomes the gradient of f at, if we just start looking at the information they gave us, they told us what c of 3 is. So that's 1, 0, 1, dot product with c prime of 3. So now we have these two pieces of information. We look up here, those are exactly the two remaining pieces of information. So f of the gradient of f at 1, 0, 1 is 2, 2, 2. And then we take the dot product with c prime at 3, which is 1, 2, 3. Okay. And now it's just a dot product. And so we do 2 plus 4 plus 6, which is going to be 12. Okay. Cool. Yeah, so this is one of these types of problems that at first glance maybe seems like it's harder than the other problems, because it's not exactly just plug into the, just like using the formula in the straightforward way. But then you realize that for this problem, we don't actually we don't compute any derivatives, right? We just plug in all the information you gave us and then take a dot product. So it's actually much nicer. It's much easier than the other problems in that sense. Okay. Cool. So let's go ahead and open 2.6. So this is going to be a little bit more about gradients and directional derivatives. Okay. Cool. I would actually write this in the other order, actually, if I think I should have written it. This is directional derivatives and gradients. At least that's the order we're going to talk about them. Let me switch this. There we go. So let's start with directional derivatives. I'm going to do the thing where I pull up the textbook definition and then talk about it. So here we have this is the technical definition of the directional derivative. Basically, what you want to take away is kind of the language they use. So it says, if we have a function, it says in 3 variables, but technically you can do it in n variables. But we'll just say 3 variables. But you definitely 3 or 2 are the ones that we'll definitely focus on. But technically you can do it in higher dimensions too. But so the language they use is they call it the directional derivative. Come on. Of f at x along v. So you need a function, you need a point, and you need a direction. That's the vector v. Okay, and it's given by this derivative. This derivative here, you can break down what it means, but really this is not going to be how we think of the directional derivative. This is a technical definition, but this theorem that I have down there it's going to be how we actually go about computing it. But the other thing from this part of the definition that I want to highlight, so the first thing was the way we talk about directional derivatives. We need three things. We need a function, a point, and a vector for the direction. The other thing is that that for that vector, we choose v to be a unit vector. Now here it says normally we choose v to be a unit vector, but I think for the sake of this class, we're going to say make sure that v is a unit vector. So I'll maybe write that over here. So over here, I'll say make sure v is a unit vector. So if you're given a direction and it's not a unit vector, so if v isn't a unit vector, then normalize it, right? Remember, you can take any vector and normalize it, and it gives you the same direction, but it's unit length, okay? So basically, let me talk a little bit conceptually here, what's happening here, why we're talking about this directional derivative. So the derivatives that we've done so far, and I have a little picture on the first slide here, have basically been like, if you want to compute the derivative in the x direction or the y direction, right? So ddx or ddy, right? This is the derivative in the x direction. This is the derivative in the y direction. I like to think if you just had a line coming in the y direction, just like parallel to the y axis, then you'd kind of carve out a chunk of the graph, which would just be a single variable graph. This derivative here is telling you what the derivative of that function would be, okay, as if it was single variables. But what this is doing is it's saying, what if I want to go in some other direction now? Okay, so if I want to go like out there in that direction, that's like, and let's say that direction is v, okay? Then what's the derivative in that direction? Well, it's going to be something like that or something like that, right? This is, d, the derivative in the v direction at this point x here. Okay, so basically, and maybe I'll have a better picture of it tomorrow morning. I'll prep something, but what I like to think is that we're carving out like a certain path in the domain, and then we're following that path as a single variable function upstairs. Like we're seeing what that path looks like upstairs, and we're just treating that like a single variable function. So far, these partial derivatives are just when the path is just the straight line parallel to x. Over here, it's the straight line parallel to y. But then we're saying, okay, what if we go in other directions? And now the reason we want to, this brings us back to the reason we want a unit vector is, and it talks about it here. This is going to affect the speed at which we're moving in that direction, the speed at which we're going along that direction. And since we're talking about since the directional derivative is a derivative, that's all about rates of change, which is all about speed, right? Velocity is, the derivative gives you velocity. So we can think of this as we want it to be moving at unit speed. So we just normalize any vector that we take the directional derivative of. And because we don't want to overcompensate by just taking a super long vector. And then that gives us, that the derivative is going to be super big because we just took this vector that goes super, super fast. Okay. And so I'll have some better pictures for us tomorrow. But that's kind of the idea I want to give here. So we're using a unit vector because we want to normalize the speed because we want to be moving at what we call unit speed, which is just kind of you could think like if the units are, if the time units are, hours and the units are miles, then this is 1 mile per hour or whatever, right? So it's 1 unit of speed, whatever your units are. Okay. Now, the second thing that's here, so this was the definition, which again was this derivative, but like I said, we're not going to focus too much on this derivative here. What I want us to use to actually compute the derivative is this formula down here. So they wrote it 3 different ways for you. I think this way here is probably the most, this one here is probably going to be the most valuable in terms of notation. So you have the gradient of f dot product with the vector in which you're taking the derivative here, and then all of this other stuff is just other ways to write that. So you could think of, instead of thinking of the dot product, instead of thinking of the gradient, you can think of it as the total derivative or the matrix of partial derivatives, which ends up being this row matrix. Or you can, sometimes they use this notation for a gradient. I don't like it as much. Takes up too much space. And then, and then this here is just exactly the same thing, but spelled out, right? If you have the coordinates for V and or I should say the components for V, and then the partials here, that's exactly the components of the gradient. So this is just exactly what the dot product is, right? So this is just spelling out the dot product here. Okay. Cool. Any questions on that? I think the next slide is going to be a quick example that I get to do, I think. Okay. Cool. So go ahead and look at, here's a quick example. So we have the derivative of this function here at this point in this direction. So remember, if you're the most straightforward way they could present you to a problem in this section is they say, here's a function, here's a point, and here's a vector. We want you to take the derivative of this function at this point in this direction, in this vector direction. Okay. And that's kind of the most basic way we can ask you a question in this section. You have to give you you have to be given 3 pieces of information: the function, the point, and the direction. Okay. Now, as you've seen, every time we introduce something like this, there's also other ways to approach. We can use this in more clever ways, like you might be given different pieces of information, but I think let's start here with just this most basic way we can ask a question. Here's a function, here's a point, and here's a direction. The first thing we should do is to make sure that V is a unit vector. Make sure V has unit length. And if it doesn't, then normalize it. So we're just going to go ahead and just check the magnitude of V. In this case, this here is V here. And so we get the square root of 1/2 squared plus square root of 2 over 2 squared plus 1/2 squared. So this is going to be equal to the square root of 1/4 plus 1/2 plus 1/4, which is equal to square root of 1. So just 1. Okay, so this one checks out. If it didn't, you might think like, oh, we wasted our time checking this length, right? But if this wasn't 1, then we can just divide all of this by whatever we got here. Okay, in this case, that would just be dividing by 1, so it doesn't do anything. Okay, so this is part of the process for normalizing. So if you didn't get 1, you would just divide here anyway. Okay, now that we've made sure that this is a normal vector, then we're just going to go ahead and compute the gradient. The gradient at f is equal to, we're going to say the derivative with respect to x, which is going to be 2xy, and then the derivative with respect to y, which is just x squared, then the derivative with respect to z, which is 3z squared. Okay, and now we specifically want the gradient of f at 2, 1, 2. So we'll just plug in these numbers for x, y, and z into this formula, and we'll get 2 times 2 times 1, and then 2 squared, and then 3 times 2 squared. Okay, simplify this. This gives us 4, 4, 12. Okay. And so the directional derivative, the derivative in this direction, is going to be the dot product of this. So we take the dot product. So we do our final answer is going to be 444 dot 1/2 square root of 2 for 2 1/2. Oh, 4412. Sorry. And yeah, and this is just going to give us 2 square root of 2 and 6. Oh, plus. These should all be plus. Taking a dot product. And so this gives us 8 plus 2 square root of 2. Okay. Okay, any questions on that? So like I said, we're running a little ahead. So if you have questions on this, it's cool. We're gonna dig deeper into this tomorrow. Okay. I'm glad I was able to get through this one example, but we're gonna kind of build on it. And I want to talk a little bit more just conceptually about what all of this means. I'm gonna talk about that tomorrow. Okay. I'll have some pictures and stuff for you tomorrow. Cool. Sound good?